Okay, we know that the gradient of a stress-strain graph is equal to Young's modulus. In this question, we're asked to show that the area under the stress-strain graph is equal to energy stored per unit volume. So the area can be determined by doing y-axis times the change in the x-axis. So in this case, on the y-axis, we've got stress, and on the x-axis, we've got strain. So basically doing stress times strain. Stress is force over area, and strain is change in length over length. And if you put those together, you get this expression. As you can see at the top, we've got force times change in length, which is actually work done, or force times distance moved parallel to the force. So that's work done, which is another way of saying energy. At the bottom, we've got cross-section area times the length, which is volume. Okay, so therefore you have the area under the graph equal to energy divided by volume. In part B of the question, you've got a stress-strain graph for material X and a wire of length 2 meters and a cross-section area of 8 times 10 to the minus 7 meters squared is made from the material X. Calculate this energy stored when the wire is stretched to a strain of 0.4. Okay, so the area under this graph, like I said, is equal to energy stored per unit volume. So let's work out the area under the graph first. So half times the stress times the strain there. So it's the triangle. Work out the area of the triangle. So that gives us 4.0 times 10 to the 7 joules per meters cubed. So that's per unit volume there. And then we need to work out the volume then. So volume is going to be cross-section area times length. We've got the cross-section area, which is 8 times 10 to the minus 7 times 2 to the length, and that gives us the volume. Okay, now we just simply have to multiply these together because energy stored per unit volume times volume will give us the total energy stored, which is 64 joules. Here we have a stress-strain graph for a rubber band. You can see in the picture there, it's being stretched. So when we put a load on it, it's following this stress-strain graph here. And the area under this would represent the work done per unit volume on the rubber band to stretch it. Okay, and then when we take the weight off the rubber band, it's going to be unloading. It doesn't follow the same path back to the origin there. So it does return to its original length, but it doesn't follow the same path. And the area under this curve, which is shaded by the green here, is the work done per unit volume by the rubber band returning to its original length. So if we had something hanging on it, it could raise something with this energy, or it can speed up something with this energy. So as you can see, there's a difference. The amount of energy we put in loading is more than the energy we got back when we're unloading. So this area that's in between the curves is the energy that's dissipated per unit volume, stretching and unloading the rubber band. So that would cause, for example, the rubber band to heat up each time you stretch and unload the rubber band.